In this example, we're going to be considering case G, the travel route example, and you may recall that our paths to get from A to B could be direct, or they could require that we travel through C. So our goal is to get from A to B, but there's two routes, either directly in the northern route or through city C, AC, and then CB. And let me just repeat all the probabilities that we were given in this case. We have the probability of event AB is equal to 2/5. The probability of, do that very well, the probability of event AC is given as 3/4. The probability of CB, and these are just the probability that the particular road is open, is 2/3. So it looks like the flakiest road is the northern route from A to B. Rather unfortunate, but that's the way it is. We were also given some conditional probabilities. First, we were given probability of event CB given event AC is equal to 4/5, and the probability of event AB given the simultaneous occurrence of event AC and event CB is equal to 1/2. And again, the event is that the particular route is open. So probability of event AB means there's a 2/5 probability that that road from A to B directly is open. So what we need is a Venn diagram, and it's the same sort of Venn diagram that we've had before. It's just hard to draw it until we figure out all these probabilities. So I'm just going to draw a generic one that won't necessarily be particularly to scale. So we're going to have one event, which I'll put as AB. We're going to have a second event, which I'll call CB. And we have a third event, which is AC. Now, we're going to be able to, we know that we can get from A to B if either one of these things is true. Either the northern route is open or both of the southern roads are open. So we need to have either AB happen or AC and CB. Now, basically that means we would be getting to the destination of B if we're in either the circle AB or in the intersection of AC and CB, this area here that I'm indicating with my pen tabs. So we need to now figure out all these different probabilities. First, let's figure out what we can from these conditional probabilities. We know this last row says that the probability of event CB given event AC, by the definition of conditional probability, means that we would have the probability of both event CB occurring and event AC occurring. This means basically that the southern road is open divided by the probability of event AC. That's just applying the definition of conditional probability. But now we know that that's equal to 4/5, and this one we were given is AC is 3/4. Then all we have to do is multiply 4/5 by 3/4, and we'd have the probability of CB and AC being open, and that's just equal to 3/5. So that is 3/5. And what that is saying is that this intersection right here between AC and CB is 0.6 in total. So that overlap of those two circles, AC and CB, is 0.6. So I didn't draw it particularly well to scale, but I don't need to redraw it. I'll just have to remember that that intersection gets up to 0.6 in probability. But I also need to know what's the probability that all three roads are open, and we can get that out of this second conditional probability definition. We can get we're given that the probability of event AB given event AC and event CB is equal to, and by the definition of conditional probability, that we're in all three, AB, event AC, event CB, divided by probability of event AC, event CB, which we just calculated. So this one we were given as 1/2, and this one we just found to be equal to 3/4. So, oops, I need to correct that. It wasn't 3/4, it was 3/5. It was our result up here. So, that's 3/5. And now we just can get that this intersection of all three then is 1/2 times 3/5, or 3/10. So now we know that this portion that I'm trying to shade right here, that's in all three, we know that that's equal to 0.3, which means that this portion is also 0.3, because we knew that the intersection of AC and CB totaled 0.6. So we know those two portions of it are each 0.3. We just found the 0.3 here. That's the 3/10 is the probability that we're inside all three circles. And then the 0.3 is the portion of AC and CB intersection that lies outside of AB. Well, I think that we're able to go through and figure out this problem now. So question A asks, what is the probability a traveler will be able to make the trip from A to B if she has to pass through road C? So if you have to pass through road C, then the probability then that southern route is open means that we'd need both A, C, and CB to be open. We already found that. That probability is what we found right here. It's 3/5, or 0.6. And B asks, what is the probability that she'll be able to get to B? Now, how can she get to B? She can get to B by either the northern route being open or both of the southern routes being open. So how we can get that is we're either inside AB or in this little smidge that is just outside of AB, but where both the southern roads are open. And we know that probability is 0.3. So it's the probability that AB is open, that is 0.4, that we were given up here, plus the 0.3, that's the intersection of AC and CB outside of AB. So it's 0.4 plus 0.3, 0.7. Now it says, which route offers a better chance of getting to B? Well, we saw that the northern route's only open 40% of the time, and the southern two roads are open 60% of the time. So the AC to CB route better. And that's our answer to case G.